So last time we finished our discussion on continuous time processes, and we did some stochastic processes, and we talked about several properties of Brownian motion. So what we are going to today, maybe in today's discussion and the next discussion as well, that we will try to define the integrals of that, how to integrate the different kind of functions and processes with respect to the Brownian motion actually. Okay? So that's what is our EM. So we last time had a kind of a glimpse that, imagine if you have this space of square integrable functions, okay? Mainly they are really the deterministic functions actually, then how to define the integral for it. How to define that? How are you gonna do the integral of of a function f from the space L to a b. Okay. So the rough idea that we had last time is that if you take a dense subspace of L to a b, so imagine S is the collection of the square integrable step functions, okay? Collection of step functions, okay? On obviously A to B, then this class of a step function contained in only A to B, but if this S is also dense in L to AB. Okay? By the way, such integrals, when f is a deterministic square integrable functions, you call such integrals as the Wiener integral. Okay? You call it a Wiener integral. So today, the first part of the discussion will talk about some of the basic properties of the Wiener integral. If you remember what we did, we started with a map I that takes a step function into AB and throws it into the space of the random variables, okay? L2 omega, which is space of the square integrable random variables, okay? And we define the Wiener integral for the step function. So if f is some step function, say with the description, obviously, what you need to do is that, okay, you take this interval A to B, you create a mash of it. Maybe this is your T0 and T1, and maybe this is Tn, okay? Then, and I have a function f that is a step function. Then the step function would look like, something like this, I equal to 1 to n, some constants ai, where ai are some real number multiplied by the indicator function of ti to ti, ti minus 1 to ti, where ai's are the real number, which simply means that in each of the ti minus 1 ti, the function takes the value ai. Okay? ठीक है जी. Okay. So we have a step function. So what is the meaning of this step function? Okay. What is the meaning of the integrating such kind of a step function? So integrating such kind of a step function with respect to the Brownian motion, and the way we defined it in a very intuitive way, that that you take this sum actually, so I equal to 1 to n is the ai multiplied by, so if f is something like this, multiplied the increment of the Brownian motion toward this time, so w of ti minus w of ti bi minus 1. Okay, so this was the map. The map is indeed well defined. Okay, in other words, that if you take the square of it and compute expectation, then the square of this and computing the expectation will give you, that would be a finite number actually. So we saw this in the last discussion as well. Okay, now the real question is that if I take an arbitrary function from L to AB, what would be the meaning of the Wiener integral for such kind of a function actually? So in other words, I would like to extend this map from S to the space L to AB actually. So I want extension for this map actually. Okay, and if I want an extension for this map, in other words, I want a map I. Okay, I can give it a different name, but let's just give it the same name I. Okay, so I want a map I that takes an F from obviously to AB and spits out the the Wiener integral, okay, of this square integrable function, and this should be indeed in this L2 omega space actually. Obviously omega is the omega FP is the underlying probability space actually. So you want such kind of a map which is going to be really an extension of this map actually. So the question is, can I achieve this extension? The answer is yes, because S is dense in L2AB, and this will be a very useful fact for us actually. So what we can do, so if I take an arbitrary, square integrable functions, okay, and I'm again saying that whenever I refer to this space, I'm gonna mean that they are the deterministic square integrable functions actually. So we are first trying to do what? We are trying to define the Wiener integral or the stochastic integral for deterministic functions. So what we can do is that, for this function f, I can find, since S is the space of the step function is dense in L2AB, I can find a sequence of step functions, and that sequence of the step function basically, in S, such that this sequence approximates the f in L2AB sense as n gets bigger actually. Okay, so this gives kind of a hint for us that okay, if you want to find the try to define the stochastic integral of f, okay, and you have a sequence of the functions, step functions, which approximates f, and we have a well-defined notion for the stochastic integral of this step functions. The question is maybe that sequence of stochastic integral of these step functions would help us to get something about something that we can treat it as the stochastic integral of the function f actually. Okay. Here is a little remark. Okay, maybe I'll just write it here that this map satisfies an interesting property that if you take the I of f, in other words, you take this Wiener integral for the step function and compute the square of it and the compute expectation, okay, then this is going to be same as the this is going to be the same as the integral of I of f square actually. Okay, so writing it correctly, yes. No, not I of f square, but this is going to be the integral, or maybe the integral of a to b f square of p and dt. In other words, if you compute the and can you see that why this would be true? Think about it. So you take this r of f and compute the square of it. Okay. This increment will turn out to be, you can already see that this increment will turn out to be what? The square of the increment will turn out to be the increment of the time interval, and maybe you will have a way to figure it out there basically. that this
partition.
yeah. So in other words, you can use this definition in using the properties of Brownian motion. You can easily show this actually. So maybe you must verify this actually. Okay. You can also treat this as, I mean, if you think, you can also treat this as that this f is L2AB, norm. Okay. So you can also treat this as that this is like the isometry actually. Okay. So if I treat I as a map from S to L to omega, then this is really one way to say that I is an isometry for such a different map actually. Anyway, so you can verify this property very simply. We talked about it last time as well, that how we can do it. So let's return back to the an arbitrary square integrable function and a sequence of a step function that approximates it actually. Okay. So the next thing that I would like to do is that, okay, for these step functions we have the notion of Wiener integrals. So let's think about the sequence of the Wiener integrals of the step functions actually. Okay. So my claim is this, that this sequence of integrals of the step functions is going to converge, and this is going to converge to a random variable, and whatever this converge, we're gonna call that random variable as the integral of the fn. Okay? So this is what is really the argument actually. Okay, so I of fn is and converges. So the question is why it must converge. In order to show that the sequence of the Wiener integrals of the step function converges, what you can show is just show it that it's Cauchy, because the other space is a Hilbert space actually, and omega is a Hilbert space. So what we can show, okay, that I of fn minus I of m, okay, and it's square in L2 omega now, which simply means that compute the expectation of it, and I would like to show that this goes to the 0 end. Okay. So what we can show, okay, you can also verify very easily that I for the step function is basically a linear map actually. Okay, it's a linear map to, in other words, if you take two step functions and talk about and consider the stochastic integral or the Wiener integral of the sum of two step function, this would be same as the stochastic integral of sum actually. In other words, I can do this. Okay, and isometry tells you that this is same as integrating, not integrating, the difference of fn minus fn square in L2 AB. Okay.
So the fourth one is what sense expectation is also norms are maybe the norm in as
yes, that's a norm in L2 omega, and I'm using this property now. Expectation of I of x y the same as the. Okay, so this must be the case. If I know that like this is a convergent sequence of step functions in L2AB, so it must be Cauchy. So this goes to 0 as and m gets bigger and bigger and bigger actually. Okay, so this shows that this I of fn is Cauchy, so it's Cauchy in L2 omega, and hence convergent. Hence convergent. Okay. So I'm putting a definition that if f is from L2 AB, okay, and fn is the sequence, okay, from the space of the step functions such that Fn approximates F in L2 AB sense. Or shall I say with the same notation? Okay. It's the same notation as previous discussion, so I'm just writing it directly. That if you want to define the integral from A to B, the Wiener integral from A to B of a square integrable deterministic function, okay, of t, then this is basically the limit and goes to infinity I of Fn. In other words, we have given this limit a name actually, and that name is this actually. Okay? So we are defining it in this manner. Now, you can obviously ask a question that why this map is well defined actually. In other words, that for a given function, it's not necessary that you should only have one sequence of the step functions. You can have multiple sequences of the step function that approximates the same function. You know, the question is that are the two different sequences of the step functions that approximates a given square integrable function would give you the same limit? The answer is yes, actually, shouldn't be a big trouble. So let me just quickly go through the argument that why this map is well defined actually. Okay? I mean, if you wish, you can also call this is I of F actually. Okay, so I of F is this is a square integrable function, and you're giving this name actually. Now, what we need to say that, okay, imagine if F has two approximating sequences in L2 AB, and you know, so you have another sequence that approximates F in L2 AB as n goes to infinity, and obviously I'm assuming that Fn and Gn are sequences of the step functions in F. Okay, so this is what is the case. The question is that are Fn and Gn either identical or can you bring them closer as much as you want actually. So you can show it very easily. So what actually I can show, so what should be done? So you need to just show that or you need to show that I of Fn and this I of Gn, they both converge to same limit in L2 omega. Okay, so they both converge to the same limit in L2 omega. Okay, and this can be very easily shown by just computing the difference actually. So Fn minus I of Gn, and so taking the square of it, and if you wish, you can take Gn term. Actually, it's not necessary that you should take always the same term and make a comparison. So you can have this, and this would be same as with the same argument. You can, but by using the linearity of the I and all the same argument, you're going to see that this would be same as Fn minus Gm square and okay, and then I can add subtract F here, okay, and apply an appropriate inequality. I can show that this goes to the zero. So in other words, I can show that this can be estimated by A to B Fn minus F square dt plus, okay, maybe some suitable constant would appear. Maybe you're going to have some 2 here, something like that. Okay, and A to B and F minus Bm square and dt, and this guy goes to 0 as n goes to infinity. Okay, so this shows that your map I that we have defined as the limit of the sequence of the step function is a well-defined map. Okay. Okay. Now you have such a map. You have such a map I from L to AB that takes an f and gives you the Wiener integral of the given function f actually. Okay. Now, what does this shows is that this I of f is basically, so the I of f is a random variable actually, isn't it? Okay, it's a random variable, square integrable random variable. So it's very natural to ask, okay, what kind of random variable would it be? So what would be the distribution of it, and what would be the mean of it, and variance and all this stuff for it actually. Okay. Then what we can show. So can you guess that what should be the distribution for this function? Think about it. So the I of f inherits everything fundamentally from the increments of the Brownian motion actually. Okay, so it inherits something from the Brownian motion. So for sure the mean is going to be 0. Okay, for sure the mean is going to be 0. The question is, what should be the variance of it? Okay, the variance of this is going to be that if you are taking f, the variance of this is going to be the L2AB norm of f.
As you've seen there.
Is it? You can't see it?
No, as you've seen there.
Yeah. We already have seen that. This must be normally distributed. So the only, the trouble that you can have is how do you know that it's normally distributed? Well, we know that I of Fn is the sum of the increments of the Brownian motion. Okay, so you have the random variables, normally distributed random variables that you are adding, and then you are taking n goes to infinity. Okay, then you have what we call central limit theorem that tells you that if you add lots and lots of random variables. Okay, IID as well. This satisfies the IID condition as well of the random variables. Then their sum is going to converge to the CLP actually. So in other words, that is really borrowed from CLP. Okay. So, but I would suggest you to have a to write a careful proof for this as well, that really this is a true case. Okay. Now, we can ask different questions.
Will there be a square on it?
Yes, for sure there is going to be square, because expectation of I of f is going to be isometry is telling you. Okay. So this identity expectation of I of f, Wiener integral of f is square being equal to the norm of square of L2AB. Like this is for the E2 isometry. So why it's E2 isometry? Can you think about it? Because you can see that this is same as saying that you have I of f, okay, in L2 omega norm, same as that f in L2AB norm. So in other words, I is a kind of a map that preserves the size of the function actually. Okay, the size just stays the same actually. So I is a map that preserves the size. Okay. The other way to say is that isometry is kind of a map that preserves the, it's a kind of a rigid motion physically, that in which the distance between any 2 points, okay, stays the same. For example, this rotations and shifts and all these are examples of the isometry, but this is a bit abstract. Okay. All right. One of the consequences of this keto isometry is going to be, a result, not just proving it, just think about it for yourself. It's just really a simple exercise that if you take two functions, say from L to AB, and you try to compute the expectation of the product of the stochastic integrals this would be same as, can you guess what should be the outcome? So I know the outcome when this G is F. Okay, this is going to be norm of this actually. Okay, so it's really going to be
different G.
you know, the integral from A to B f of t dt. Okay, so in other words, you are just saying that obviously L to omega and L to AB both are Hilbert spaces, so you have the inner product on it actually. So you are saying that you know the inner product of f and I of G over L to omega is same as the inner product of AB actually. Okay, so let's give it a go that why this must be true. So another remark that I would like to have next is the case that you know I know that I can't you know define the stochastic integral you know of some kind of a function, for example L to AB, in Riemann-Stieltjes sense actually. The question is there a way, okay, is there a way that you can relate these two notions actually, this Riemann-Stieltjes and you know the Wiener integral or the stochastic integral. Why we are not able to define, for example, integral of a function, for example, with respect to itself because of the variations actually. Since we don't have variations of a function, even if you can have a continuous function, okay, you can't define the Riemann-Stieltjes integral. So I would like to make a remark, okay, let me just quick hint that, I mean, if you have a function that has bounded variations, then there is no difference between Riemann-Stieltjes integral and the Wiener integral actually. So you can interpret it in the terms of the Riemann-Stieltjes actually, okay. And you know this means that you can also simulate it on computer, because think about it. We know how to simulate, you know, for example, or how to see a integral, you know, when it is in the Riemann-Stieltjes sense actually. Okay. In next class, yes, bring your computers with you, okay, because I'm gonna say another chap, he's gonna go through with the simulation of at least some basic stuff about the Brownian motion to you, that how to simulate this actually, how to do that. So in 1 hour course, 1 hour class actually, okay, 1 hour class that we have on Monday. So bring your computers, if other simulations. Okay, so here's the thing. So imagine f is f be a continuous function with bounded variations, okay? Bounded variations, first order variations actually. So we defined last time variation. So it's a function, okay? We defined it properly, okay? You can define it as, roughly it was a series actually, and what you are asking about that, does this series converges to some function or not, and that function would be the variation. So if we have a function, so f is the kind of function that has variation, and those variations are bounded, then for almost all omegas in omega, okay, if you take this random variable, f of t, twt, the Wiener integral, okay, and evaluate it, would this make sense actually? So if I have a continuous function, is it going to be in L to AB? So I'm not assuming f to be in L to AB, so I'm saying it's continuous actually. Would that be square? Anyway, so this makes sense. In other words, you take a continuous function with a finite bounded variation and compute its Wiener integral. Okay? I know this is a random variable, so I need to evaluate it at omega. The question is, what should be the output? The output of this function is going to be the Riemann-Stieltjes integral. Okay? The Riemann-Stieltjes integral of the function a to b, f of t, and d w of p. Okay, so that's an integral in Riemann still sense actually. So I know that how to define it. So in other words, you take your interval, partition it, okay, you know, and on each sub interval, say for example, compute your f of t at say for example left